So far, we've ignored the whole problem of how do you start a forecast? How do you initialize the parameters you're going to use? The level, the trend, the seasonality. Let's dive into that now. And so the big takeaway, or the big point for initialization, there's no single best method. There are many good ones. And as the simpler the exponential smoothing model, the easier the procedure is. The most complicated one is the Holt-Winters, we'll talk about in a few minutes. One other thing to think about is the data that you use. You're going to need 3 separate data sets to really set up one of these models. The first one you're going to use to initialize the data, to come up with your initial estimates of level, trend, and seasonality, if you're using all 3. Then you're going to need another set of data to train it. This is when you introduce the smoothing factors. You want to determine, should I use an alpha of 0.1, a 0.15, a beta of 0.001, 0.05, whatever. You want to figure that out during the training set of data. And then after that, you want to test it. You want to see how well it does on a new set of data. So this requires a lot, and in many cases you won't have all of this data, but you should try. It's a dangerous thing to initialize, train, and test on the exact same data set, because you'll probably overfit the model, and you'll end up with a very high alpha, a very high beta, because it's trying to match exactly what's happening. So we'll talk more about this in our next set of lectures, but let's go through it and say, how do you initialize? Let's start with the simplest model. Simple exponential smoothing model. All I've got is a level parameter, an A. So how do I find this out? Well, I look back and I find a bunch of the most recent periods, 5, 10, whatever I have, and just take the average. Average demand, done. So that's the easy one. Holt model. Now we've got both a level and they've got a trend, so we need to find those initial estimates. So this is actually pretty easy too. We're going to find this by using ordinary least squares regression, which we're not going to talk about in this video. We're going to talk about next week in detail. But essentially, it's a way to find the best linear equation to fit a data set. And it's ordinary least squares minimizes the sum of the squares, and we'll talk much more about this. But essentially what you've got is a regression equation where your demand, the actual demand that happened, you're going to fit this equation, beta naught, which is the intercept, plus beta 1, which is the slope, times t. So you're going to end up with estimates of your A and your B. Now we'll talk about this in depth on the next week, but what we're doing is giving equal weight to each observation in that data set. But we'll talk more about this. So this is regression. So for the Holt model, when all you need to estimate is a level and a trend, ordinary least squares regression is the fastest way to do that. Okay, now it gets a little more complicated. We introduce seasonality models. So there's different ways to do this. The big overarching need, though, is more data. You have to have at least, obviously, 2 seasons worth, but it's best to have 4 or more. You want as many as you can have, but then you can see you're getting into a trade-off. As I get more data going further back in my history, it's probably less relevant to today. But you want to be able to get multiple data points for each point in your seasonality. So let's look at the first one, double exponential smoothing. And this one makes sense. This one's a little easier than the Holt-Winter one that we're going to talk about in a second. So we're going to have to estimate 2 parameters, the level and the seasonality indices for each of the seasonalities. So if I have the 4 periods here of the sandwich shop for bagels, the daily bagel demand, right, where this is a Monday, this is a Monday, this is a Monday. You see it goes every 5 days. You see the seasonality. So if I have this history, how would I figure this out? Well, I want to find the average demand for each day, in this case, each common season period. So I find the average demand on Mondays, the average demand on Tuesdays, Wednesdays, etc. Then I find the average demand for all the periods, right? I've got that, and then I simply divide. 60 divided by 121 is 0.5. 90 divided by 121 is 0.75. So I'm finding what a Monday's sales are as a fraction of the average. And this will naturally have to sum up to P, in this case 5. And it'll average to 1. So this is pretty easy. We just find the average each day or each period and then divide that by the average over the whole length of that historical initialization data set. Okay, but here comes the tough one, Holt-Winter. So there are many methods out there. We're going to talk one that's called the P-centered moving average method. And what we're going to do is I'll talk it through the exact same example. We're going to first find the seasonality indices, because now what we've got for Holt Winter, remember, I've got a level, a trend, and seasonality. So first thing I do, I have the data over here, and you see I've got 4 weeks of data. Every time period is listed on each row. The day of the week, actual demand is listed here. And then what I'm doing is I'm finding a moving average of 5. Why 5? Because that's P. And so I find this moving average, and I have this 128.3 is the moving average of these 5 time periods. So I centered it. That's where the center comes from. So then the next one I do, let me just erase that, 129.4 is equal to the moving average of these 5, and so forth. So essentially I'm doing a moving average and then shifting it up to be the first one to be centered in that period. Now if I have an even number of periods in my seasonality, it gets a little more complicated. You want to do one on one end and then the other end and average it, but this is a little easier. So I get that moving average. So essentially what I'm saying is on Wednesday, let's look at one, time period 82, actual demand was 163. The moving average around that said it was 128.3. So if I want to find my seasonality, all I want to do is divide my actual demand by that estimate. And this is the estimate of the level. And so what I'm doing, I'm de-leveling it. And so I'm saying, well, you know what? That says Wednesday has about 27% more than the average day, or 1.273. Same thing with, let's pick another day. Let's pick, the next day, Thursday, time period 83. 129 was the actual. If I did a 5-day moving average around that, where this is the centered, right, 5-day, right? So it goes 2 days before, 2 days after, and that day, it's almost even. So that's kind of like an average day. So I do that for each of those 5 periods, and I end up with this center point moving average column. That's what's in this column. And then what am I going to do? Well, what I want to do, this center point average is this line, by the way, on the chart. I'll just highlight it. So that's what I'm doing, because I'm trying to de-seasonalize things. So I ended up with this estimate of the F1s, where I just divide the actual divided by that center point average. And what do I get for that? Well, each one of these. So now I go through and I found it for each period. Now I'm just going to sum them up. Let me sum up all the Mondays. 0.492, 0.518, 0.495. I take the average of that and I'll get 0.501. I do the same thing for Tuesdays, right? What's a Tuesday? 0.735, 0.736, 0.752, etc. And so I do that for each of the separate days. So once I get them, chances are it'd be an exceptionally rare thing for them to sum up to P. They don't in this case. They sum up to 4.952. I'm a little low. So what am I going to do? I'm going to normalize them just like I did in the previous video, and I'm going to increase them all a little bit to cover that, 0.048 gap to get it to 5. So each one of these is normalized. You'll see they each go up by about, about 5 units each. So it depends, and then it sums up at the end of the day to 5. All right. So that's the first step, first 2 steps. The next thing we want to do is estimate the initial level and trend values. And so from here, what I want to do, what I've done already, is, and this chart still shows the week, the time period, the day of the week, the actual demand, and then this is the normalized indices that we just calculated, right? We just calculated, you see they repeat each week. And then what I want to find is the deseasonalized demand. And all I'm doing is taking the actual demand in each period and dividing it by my seasonality index that I just calculated. And so what I'm finding is this line, which is the deseasonalized line. I took seasonality out of it to try to find the level and the trend. Okay, so what am I going to do to find that now? Well, I've got these data sets, right? This data, and I'm trying to find an A. Well, actually, I'm going to be doing it from time period 100 forward. So I want to find an A hat 0, which is my intercept essentially at 100. And I want to find what the slope is, a B hat 0. So how do I do that? Well, we're going to use ordinary least squares regression, just like we did in the previous Holt model, where it's just level and trend. And so we'll talk about the details how to do that next week, but you end up with this equation that the intercept at time 0 is negative 216.9 and the slope is 4.192 bagels per day. So I'm starting at time period t. T equals 100, so I'm going forward from there. So my initial estimate for the level is going to be that's this equation, right? This equation we just calculated. And I'm going to multiply that slope times 100 minus 216.9 gives me 202. Then for the slope, I already know what that is. That comes out of the equation, 4.192. Call it 4.2. So I've got my A hat. This is my B hat 0. And down here are all my estimates for the indices, the seasonality indices that we've already done. So it took a long while to get to it, but hopefully you saw the mechanics of it. And all we're doing is getting a first best estimate for what these parameters are.